So, nice to see you. Nice to welcome you to Network Security lecture for the master courses. And let me first introduce myself a bit. So I'm professor since roughly a year here in Bingen for networks, communication systems, and cybersecurity. Before I've been principal scientist at the Honda Research Institute. It's a very nice environment if you want to do not just vehicular-related research. They are also doing lots of research in the domain of machine learning and data processing, robotics. Before I did my PhD in, so I studied computer science and mathematics, and I did my PhD in electrical engineering and information technology. I had also a focus on IT security. Have been for some time in the theoretical computer science domain, and after that I've been junior professor for 7 years in Düsseldorf, focusing on distributed social networks. Okay, so let's see what you are facing now in this lecture. First of all, some words on the organization. It's all on OLAT, so I think the slide set is anyway uploaded. So I will put all the documents on OLAT. So the link will, that you might already know. We have the lectures Mondays at 10 o'clock here upstairs. And we have some lab exercises that they will take place in L1 130. And they, actually we have 14 weeks until the end of the lecture. So these will be 7 lab exercises in total, and each lab exercise takes 2 weeks. With 9 time slots, that looks a little bit too much. So we have at maximum 4 time slots. Let me just show you what I mean. If we open, let me just open our time plan, time schedule. So let's have, if we have a look at this kind of time schedule, with Mondays we have here our lecture at 10 o'clock, and Tuesdays we have our 2 slots in the afternoon. So that means that every 2 weeks we have 2 time slots, and because it's 2 weeks we have 4 time slots. Okay? But you just need to visit 1. And the reason why we have 4 time slots is you will also see that I think out of 3 out of these 7 lab exercises, they will have the issue that our Thursday will be blocked. There's some public holiday and so on. So you will face the issue that sometimes you just have two time slots. But that's okay, because at once in that room, at maximum 19 people can fit. Let's better count for 18 or 17. That's a little bit more convenient. But if I just count and also through the numbers that I see in Campo, that should be sufficient. I will talk about the lab exercises soon. What I will also do, and this is somehow, you need to know the pros and the cons. So what I also do, as you see, I have here my microphone, I have here my recording tool, and I'm recording also the lecture, so to put it online. You find here the YouTube playlist that will contain all the lectures that I record. There are also some other lectures from me online on computer networks, peer-to-peer networks, mobile communication, maybe also network security, and some other stuff lecture related. So sometimes when I say this, the lectures will be recorded. Some majority or some people might think, oh, that's great, see you then at the exam. And I also had cases when the lecture initially had 100 people, and then once I announced that it's recorded and put online, then only 20 came, and I was thinking, what's happening now? Where are 80% of the students? And at the exam, they were all back again. I want to communicate to you that way. So this is an offer. So I highly recommend to visit, to join the lectures here in presence, because then not only you can speak with your fellow neighbors and can discuss when you didn't understand something or explain and learn through that as well, but also the interaction might be better what you take away as information with you. So it has benefits to be present here. On the other side, I also I like to offer this kind of recording in that sense. So if you want to later look up some kind of information, some kind of topic you did not really understand, you want to repeat somehow, then it's still convenient to have the opportunity to have a look at it, and nevertheless make your notes yourself. So the best way to benefit from the lecture is when you have the printouts, let's say from the lectures, you make your own notes by hand, you summarize it yourself, and I can highly recommend for everyone for the exam. That's a very nice best practice. Create maybe a 2-page, so one DIN A4 sheet of paper, maybe 2, of your summaries in your own handwriting of the topics that we had, of the most important parts. Write your own sheet of summary, and then don't use it in the exam. That's but by writing and summarizing for yourself, by finding your own words, by making the decisions what to write down and what to leave out, how to compress into tighter writing form, somehow what to draw. By that thinking process, you really think through the topics, and it helps to learn. And then basically, once writing that kind of sheet is best for preparing for the lecture. Okay, so let's talk a few words on the lab exercise, or is it? No, first the lecture contents. So we have, I think, 13, 14 lectures in total that we talk about. And I will try to sketch you a variety of topics that go beyond the regular IT security lecture, but with a stronger focus on networking. So obviously we will, and now in this first lecture, repeat to have a summary on networking and what kind of basis we start from. And then we talk about really potential attacks on networks, where they can happen, how to, what kind of measures of protection we have that you will regularly see happening. And then we talk a little bit about worms and how they spread. So these are network-related, network worms, network-related vulnerabilities. We talk also about some general process of building secure networks. And as you see, and then also talk about confidential computing. So this is a wider mix of topics rather than focusing on individual network protocol security solutions. The reason is, once you understand how the concept is of building secure protocols, you see the pattern repeating every time. So if we talk about 2 secure network protocols, 2 or 3, 3 let's say, then we can abstract the process, the pattern, and then we don't have to do it for 10 or 11. So then we can have a look at in general different other kind of problem cases, and then understand the patterns there, and then basically it's helpful to gain insights into the main solution techniques in various fields, rather than digging deep into one specific field, but that to very high detail. So one element we will also talk about is confidential computing. That describes, and this is getting more and more important for industry, as data privacy laws are very important and strictly enforced, and they can create high punishment sums that companies have to pay when they lose data. So the question is, how can companies compute on data of their customers? So for example, let's take some random automobile vehicular manufacturer, and they want to compute how long is the battery lasting how long are the distances that the cars are driving in general, in average. So what kind of distribution do you have? So you want to have some distribution with the average, with some standard deviation and so on, but you are not allowed to learn the values of individuals. So as it is with voting, you want to get the vote results, but you don't want to learn what one individual voted. And there are different approaches for this, how to implement it, that we will look at, because it has lots to do with networking. And then decentralized systems, it's a very big topic as well. So we will look in different topics and then try to pick out important ideas in these domains. Okay, so far for the lecture content. The first slide is already uploaded, so this one with 34 slides. The rest will come. It's still a little bit in motion. Okay. So far for the lecture that we have every Monday. And then the lab, that's a little bit special. So we have this kind of lab exercise. The lab exercise is, as you can think of it, we have 7 time slots where we have 2 weeks. Then the European Soccer Championship finals are and the lecture is over. So around 14th of July. So we have 7 weeks and 7 2-week slots. And in these 2-week slots, there are 2 Thursdays, surprisingly. And the ideas we have in these 2 Thursdays, in total 4 time slots. So what you need to do, so we have these 7 lab exercises, 2 appointments each. You have to register only for 1 appointment per lab exercise. And the idea is to do the following. I will jump back to the slide in a minute. So what will happen is basically on Monday of that 2-week period, I will upload in general this sheet containing tasks and questions. Please download it. And what is important, upload the document with your answers until the deadline. And the deadline is at the end of the 2 weeks. So you have 2 weeks time to download it and to fill it out. And basically this is the important part. You should download it, you should read the questions, you should do the tasks and then upload it. And in general, it is good to have the environment to do the tasks. So the network lab in the building 1 in room 310, there are 19 PCs and there are some setups possible. Sometimes it's also required that you have several PCs, so therefore it is recommended to come there and do the exercise as the environment is prepared. So ideally you register for an appointment, you come to the appointment, that is a good choice. Perform the task and answer the questions. If you don't finish in time, no problem, just do it later, I don't know. Meet fellow students, work together, ask questions. This is the important part, so to upload the document in time, in OLAT, in OLAT, with your individual solution. And to be honest, whether you do it in the lab environment or whether you do it at home, what might also be, that's also possible, it's up to you. But if you are not familiar with setting up virtual machines with Linux and then probably also having 2 that are networked, and who of you is using Linux? Very good. 1, very good. Maybe 2, okay, but that's maybe 3. It's about the majority. So last year there has been 6 lab exercises. So now we introduced some one before, in order to have some kind of tutorial on Linux, how to install software, how to navigate through the folders, how to create a file, how to edit it, how to look up config files, how to find out what to use, because most of the programs will be basically Linux related. So therefore this lab number 1 will be Linux related. the lab doc, so this task is not yet uploaded. Sorry, I did not make it in time. I will work on it today, but no problem. I mean, the first appointment that we have is not even this week. We will have it next week, as you will see. That's just, yeah, today, no, sorry, on this Thursday we have a week, we have one time slot, and next Thursday we have a time slot. Let's show it. Then it's easier to talk about it in OLAT. So let's get here. Then we go to lab schedule 1. There are 5 seats available here, 19 seats available. It's basically this week and next week. Yeah. Okay. So we should have, at worst case, 38 places. Please try to not fill out exactly 19 places. I'm not really sure about the 19th. 18 I'm sure about, but the 19th spot I'm not really sure. So I see you could register, and if you have tomorrow some problems in accessing the lab material, let me just see. Either it's here. No, I will put it under lab material. So it will be somewhere here, and in addition, probably at the lab exercise, it will be also here. Let me just see how it looks like. I have to. Can you see the lab exercise? Because can you access it or not? Because I'm not really sure whether I can even in.
Last year.
Okay. Yeah, I have to update the dates. I have to put in the file. So tomorrow it will be fine. No problem. As long as you have your schedule and you have registered, that's fine. Okay. Good. So what will we do? What will we be doing? Stop your excitement. It's there's time for excitement enough. So what we'll be doing? So the tools that we will use are also available for other operating systems. But honestly, I mean, every operating system and every tool, so we will look into different elements. Everything okay? Any questions? No? Good. So I'm not really so we will test various programs and the effects of it and see what kind of harm or good they can do. And we will be using Linux. I mean, if it's advisable to use either a lab PC, or if you test it on your machine, highly advisable, don't use it on Windows or so without virtual machine, because it might break things. So especially if first or second the lab exercise, we plan to also change the DNS server or to modify the path that the web request goes to an HTTP request, and if you don't reverse it afterwards, then you cannot visit websites or so. But probably it's also, so you cannot. I mean, you should have the ability to revert back to a functioning state, and if you are doing it on your machine, it might be difficult. So therefore, it's easier on the lab PCs, or if you are familiar, if you want to do it on your machine, to use a virtual machine with Linux on it. Okay, the first part will also be not just to learn about Linux, but also to learn about how to download a file, insert the screenshots, and upload it. But I think that will be doable. The lab computers, they have some naming, the important part, but it will be also written out. Login is Kone, and password is also Kone. Yeah, that's right. And for exactly this upcoming lab number 1, so it starts today. I mean, these 2 weeks are starting now today. The first lab we will have on Thursday. The second one next Thursday, and it's just important that until the end of the 19th it is uploaded until midnight, and the solution will be then released after that. Possible dates are this week or next week. That's not right. That's German writing. 13:30 p.m. So I think it's clear. So please register for an appointment. So for this kind of time schedule, please show up on that date. I will check how to give the option that you deregister yourself in case that you cannot join. That during the time, implement the assignment and upload the solution during the time lab time, and or in post-processing at home. Yeah. So far with regard to the lab procedure. Some of you already know the process, and it's a fun environment. And any questions with regard to that? So we will have lectures. We will have this 7 in total lab exercises, and part of the exam that will be obviously afterwards will be topics from the lectures and from the exercises, from the lab exercises. So there's nothing, and also. Yeah, my approach is, if you see any exam question, the answers are all printed either on the slides or in the exercise solutions. Then it's much easier if there's some conflict to point to. That's written, there's the question. But that was never the case, so everything is good. Okay. So we are talking about vulnerability, security issues, and obviously ways to misuse that vulnerabilities, to hack it, to attack that vulnerability, to gain some advantage. And there's some important message on the ethical basics. So we want to learn how to protect. So we want to learn what weaknesses the system have. We want to understand how an attacker can attack it. So in order to know what we can do in order to prevent it and to counteract. So we must know how attackers proceed. So therefore it's important we learn how it's working, but please don't do it. So even if there's no real damage, even if it's just a joke, even if you just want to test something, there are different laws that are very strict. And it's very difficult to have an overview which is applying, which not, what's allowed, and you enter a risk of doing something against the law if you try to run an attack. But do not destroy your own future. Yes, keep your fingers away from attackers. So better to ask, to clarify before doing some activities. On the other side, I mean, the network lab is set up in a way that that it's somehow protected also against the Bingen network. So the potential damage that can be caused might be lower than as you would if you were operating in some other network device of the university. So therefore we have some kind of protected environment, so that mistakes can happen under guidance. I mean, I'm also there, so that you don't have to fear that doing the lab exercise will cause you damage or so, as long as you follow the guidelines of the lab exercise. Okay, so let's see what kind of assumptions we have. This is a master course, so we have some kind of assumptions what we build upon. What kind of previous knowledge is assumed, and because network security, we have the combination of networks and security. So let's ask by a different approach. Who has not heard the lecture Communication and Networks, or some kind of networking lecture? Is anyone there? Good. And IT security, anyone that did not listen to the lecture on IT security? Also good. Did anyone hear both of them? Okay. So now this is a challenging question. So okay. So now I'm confused. So not networks is 0. So there's no one that didn't listen to networks. Not ITsec is also 0. So I would assume everybody listened to IT security. And networks and IT security is 3. So, but we have more. So is my okay? So I would assume network security was heard by everyone. Is that right? Networks? No? Yes? Yes? Okay, so this is equal. IT security has been also heard by everyone? No? Okay, okay. That's good. Okay. Aha. So the question was, whom of you did not listen to IT security? 1, 2. Okay. So, but then I would assume, okay, if so, whom of you have listened to networks and IT security up to now? 5, 6. So what's with your situation? So did you hear networks? Yes. IT security? Okay. Okay, then I understand. Okay. So just to understand, so there are more people who didn't had some background on IT security. Okay, good. I understand. So okay, then we will put a little bit more effort on that as well. No problem. There are a few building blocks that we need to pick up, but we will not go as much in detail how it works internally, probably more on how we can use it. So, basic knowledge of operating systems. Let's see. We will go in the next slides over a rough summary on the background, so what kind of knowledge we need from the networking. Okay, that's good to understand. So I will put a little bit more emphasis on IT security in order to understand what we need. Okay, let's go quickly through. Let's go through networking and see that we have the same view. First, some motivation for network security. So, yeah, where is the world progressing to? So we will have a more and more networked world, where we have smart cities, smart homes, smart grids, so the electricity will be also smart. Cars and mobility will be smart. So we'll have lots of, so what is smart meaning? That means we have lots of sensors around in the world, such as in buildings, such as at home, such as in cars and everything, hospital. There are lots of sensors everywhere that are producing and capturing data. The data from the sensors have to go somewhere. So typically, here it's depicted as cloud services and platform. They get all of this information. And then what we also have in the world are some kind of actuators or some kind of information panels, so basically where the impact of the information is then presented or having some influence. So for example, if the sensors would show that the window's open maybe, then the heating thermostat that is now on 5 should probably be reduced to 0 because it's heating out of the window. So there are both sensors, ideally, here not, that capture what the situation is, such as window being open, such as heating being on, such as door being open, some temperature measures. And somewhere this information is brought together through networks. There it's analyzed and decisions are made let's say the thermostat should be reduced to 0, the shaders should come down, I don't know, any kind of potential reactions. With cars, it's easier to comprehend. So if you have sensors for speed and pedal pressure and steering angle and so on, and some camera information where you observe that there's some congestion coming, then the reaction would be to hit the brakes or to reduce the speed, to modify the steering. So networking is bringing together both the sensors in the smart environment, SmartX, as well as the potential reactions to it, either by presenting it in nice dashboards or so, keeping track of the measurements, or to have direct influence on what should be changed, what reaction in the world should be happening based on what the sensors are presenting. So that's everything will be networked basically in the near future, because there's so much potential also to use, especially in the analysis of the data, some kind of artificial intelligence. So here everywhere you have networking, bringing data around. Sometimes it's time critical, sometimes it's not. Sometimes you need bandwidth, sometimes, I mean, there are various different kind of challenges or networks in this scenario. This is just one example. Obviously, you have networks also in the regular environment, online banking and so on, visiting websites, buying stuff. And these kind of networks, everywhere where we have these networks, we also have the potential, especially if it's wireless. Let's say a few words about wireless technology. We just had it now in communication networks 1 hour before. The property of wireless communication is if you have one sender, the recipients are all in the surrounding. So everybody that is able to hear that kind of signals is able to process it. And that could be challenging. For example, again, vehicular use case. It is possible that cars can be stopped during the driving around, or power voltages, that's the smart grid, or malware targeting industrial control systems. I mean, there are so many use cases where communication between two parties over the internet has been interrupted and aimed for attacks, that it's not even reasonable to pick out examples. So every time you try to do some online bank transfer, then over your bank, that's where you need to be protected against potential attackers. Or if you want to buy something, then you want to make sure that the price that is shown and the money or the confirmation that you want to buy it is correct, that you confirmed it and the price is also correct. If you send email, typically you would like to want that only emails from you should be sent in your name. Probably there's less what is done nowadays. Or if you visit the website, you want to make sure that what you type in and what is transferred, passwords for example, or I don't know, your secret bank account details are only visible to you. So there are so many examples that basically everywhere when two parties are involved in the communication. So let's see, what does it all mean, network security? So it includes all measures for planning, ensuring and monitoring of security at the moment. That's a little bit redundant. So, and monitoring of security, so it's like this, and networks. So we want to plan, we want to ensure, somehow monitor and enforce security networks, meaning secure design of networks that we will look into. So how to set up networks from scratch if you have the ability to do it. What kind of general approaches should you follow? Then securing transmissions path through suitable protocols. There are two approaches. as networks. I will show it on the next slide. Basically, it's communication over, let's say A and B want to communicate. A is in Bingen, B is in Sydney. The message has to go over several hops to reach the destination. You can secure this end-to-end communication, but you can also secure it hop-wise. What else? Then this is somehow related. If we have some kind of network setup, how do we separate basically interest zones in the network? So typically you have some kind of home network, and then you have the internet, let's say, the malicious one, then you have some company network. So how do you separate these networks in order to make sure that potential attackers from the internet do not enter your home network or your company network? How can it be done technically? How can it be done operationally or organizationally wise? And let's say this is all about design. This is about somehow enforcing. And how can we get information from the network? What's happening? Because typically there are, billions of packets traveling through the network every time, all the time. And there are so many individual data points that you could observe that's really difficult to make it systematically. And especially what is not possible is to keep a log of network traffic that you had. Because the network traffic is so huge that keeping logs of it would just expand all your available storage space. You have to basically monitor on the fly and try to identify potential problems while the messages are sent. You don't have really a strong history that you can refer to going back. Okay, so let's have a quick look at networks and what networks are. So first of all, how is a network structured? Yeah. So how we can model a network is typically, and maybe I just opened the next slides. Let me just see. I had here a nice slide just 1 hour ago in Kone, how the network of network looks like. Not here. Sorry. So basically what we have is we have a set of, let's take this image. We have it on the next. Okay, doesn't matter. So what I want to show is what we typically have is, first of all, some kind of edge of the network. So we have some end devices. These can be notebooks, this can be smartphones, this can be desktop PCs. Typically everything that has some kind of layer application, transport layer, layer 4 and level 5 implementation. So there's application layer implementations, and there's layer 4, so TCP, UDP is implemented because on these machines programs are running that are able to send out messages, that are able to receive messages. Then we have some kind of internal network that is only required for routing. So basically this is then in Bingen, this is then in Sydney, and in between we have the network, we have the internet, which is basically consisting of routers where the message is going hop by hop through the network. So, and what kind of access networks do we have? So, looking at how we can connect the networks, so there we have different distances that we are talking about. First of all, we have this PAN, so personal area network, such as the smartwatch or smart shoe, I don't know, and there are many smart things that you can attach to your body to measure some information. The next level, I mean, this is probably 1 to 2 meters at this at max distance. Then we have the local area network up to 100 meters. Typically, if it's cabled, then probably up to 1 kilometer. If it's wireless, then 100 meters. And this is the local area. Then we have, that should be an M, metropolitan area network, where we have typically the range of reaching streets or small cities. So for example, here's a smart meter that is able to measure, let's say, water usage, electricity usage, and that can be contacted from outside. And then we have wide area network, so WAN, which is basically, so in this metropolitan area network, there's also something like 4G, meaning cellular communication. And in wide area network, that's really over state and continent wide, the whole network, the whole internet. Okay, so once again, what parts do we have in the internet? And that also relates to where potential issues might be. So we always have to think what kind of challenges and what kind of attackers we might face in this direction. Oops. So first of all, there are billions of connected computing devices. So we have all these notebooks, we have all these smartphones, some data centers here, some servers there. And typically applications such as email, they want to communicate directly. So this smartphone wants to directly communicate on the application layer with the email server. And the question is, obviously, as you see, if the messages are passing through here, what can happen? I mean, is the message that our user A wants to send to server B really arriving as the user A sent it and is only read by server B? And that might be already some problem. So if potential attackers in the middle of the network would like to modify messages, to throw away messages, to read messages, what we also have here is that there are really billions of computers outside. So if a set of computers now organize themselves to send messages to one single node, then the traffic that they send would be so huge that this single node would not be anymore available, or is not able to process regular messages. Especially this is dangerous if they send this to servers, so that the servers are not anymore responding to regular questions. That would be a denial of service attack, just coming from the large number of potential devices that can work together to attack such a network node. So this is the edge, this is the outer part of the network. Then we have some kind of routers or switches that are only in the middle of the network, and their part is basically to forward messages. So they don't receive it. They are not addressed by messages. The two parties of the message are the sender A and the receiver B, and the router's task is to forward it to the next router that is closer to the destination. And for that, they have also these communication links of any kind. Basically, in the typical router has several ports, several links that it connects to other routers, and every time a message comes in, it has to decide to which other ports, to which other links do I forward this message to in order to bring it closer to the destination. Yeah, and finally, there are these networks where basically we have some kind of mobile network, some local network, some enterprise networks, data center network, and they are all connected to some kind of internet service provider. And the internet service provider, they they don't have any kind of edge devices. Their only task is to be connected to other internet service providers, such as here, and to forward the messages to the best option to bring it closer to destination. Yeah. To bring it a little bit further, yeah, let's keep it this way, probably. That might be at first be okay. So what challenges we face? We face at every point where we have one-hop communication some issues. That means, let's draw this again. So if we look into, so every part of the communication needs to get some attention. So for example, here in the mobile network, what do you think can go wrong in the mobile network where the aim is to have different nodes connected to the mobile, let's say, access point, and they want to send messages from their device to the internet? What can happen with the traffic in such a mobile network, or with the participants of the network? So let's say you want to send some bank details. You want to send a bank transfer. You want to submit money to somewhere, and your messages contain this highly highly critical information, and you establish a contact to the access point, and now the access point should forward to the router so it enters the network, the internet. What could go wrong? Yeah?
Because it's wireless, other devices should receive the same messages that the tower or receiver receives.
That's right. So wireless networks are in general set up a way that because you have one general antenna, you transmit in all directions and everybody can see what you send. So we also did once a study on this where we had the use case. So actually we once built an app that had some kind of file sharing functionality for smartphones. So basically you walk around and you have an app, and if the other participants have the app as well, then you can basically say, I want to share this kind of folder, and the others can tell their interest. Let's say I'm interested in movies, and then you walk around and then the networks establish connection to each other, the smartphones, and transfer the fitting files. And we were measuring, if we already transfer the file once to one smartphone, there are other smartphones nearby, how many of the smartphones nearby can, through just listening to it, reconstruct the data. And it was quite good. So of course, depending on the distance, I think 80–90% of the data could be reconstructed well. So that's how well you can hear that kind of information. Yes, so part one, somebody else that you are not intended to receive the message could also receive it. What else can go wrong? Yeah?
I heard that a malicious attacker can bring his own mobile tower.
Yes, very good. So you have maybe then a fake mobile tower. That's right. There was just recently I've been watching a nice documentation on that. So if you go to some Starbucks cafe and then you create a network with the same name and have this login page for Starbucks Wi-Fi, I don't know how it works, and then the people start to enter your their login details, and you are in addition connected to the real Starbucks network. So basically you are just pretending to be the Starbucks. Then you can get all their access credentials, login password and so on, and still forward their regular messages on. Yes. So in this case, the sender or the node, the smartphone connecting to this access point, did not verify the identity of the access point. So whether to whom it really belongs. So we had the problem reading messages that are not intended for so there are many recipients and they should not be able to read messages that are not intended to them. And we should verify the identity of communication partners. What else could we have? Yes?
The wireless connection might, let's say you have a really important connection, and it could be disturbed by someone who sends like same frequency, and then they can communicate with each other.
That's right. So somebody else could modify, maybe through interference or some kind of signal processing at the right times. It could modify your files, your data that you transferred, either so that it cannot be read anymore, or if it would be very sophisticated, probably changing the right places in your communication through the interference, that you transfer the money not to the person you intended to, but to the attacker also. So modifying messages is one issue, and stopping basically the functioning of the service by blocking communication. So for example, in jails, so if people are incarcerated, sometimes there are also so-called jammers, which send out in the valid frequencies as Wi-Fi or as mobile communication would communicate in all the time some signals. So if somebody is trying to communicate in the regular smartphone cellular communication interface frequencies, no signal will be able to pass somewhere, because every signal is basically overlapped with some kind of jam signal, with some kind of signal that's breaking the readability of it. This is one option, and the second, what can also happen is not just that. Let's say you have a smartphone that is connected to the communication network, to the access point, and it can send frequently messages, but every message is blocked or attacked. That's one point, but you could also throw that single smartphone out from the connection list of the access point. So you could, in the name of the smartphone, say, I'm leaving the network, please don't contact me again. And it does not have to be the initial original smartphone. There are also some kind of watches. Let me just show you one example. So actually, I'm currently supervising one bachelor thesis in that direction. That looks like of somebody who's having a very interesting YouTube channel on this. I don't know. It's interesting what students can do. So, and basically, this is some kind of watch, and you can select basically the network that you want to address, that you want to attack. And once you are in the network, you can select which which client, which connection partner you want to throw out of the network, and then you can send a false message telling to de-authenticate to leave the network basically, and then that's not anymore part of the network. Very fancy watch. So, okay. So far. So, and they are actually, let's see. Yes, okay. So some more words on networking, because now we were just touching basically the edge of the network. Then we have also the packet switches, which are in between. Their only goal is basically to use the links they have to forward each incoming packet closer to the destination. So how could you attack this? So could you take a negative impact on this ability? So, I mean, yeah, a message comes in. I don't know, So here a message comes in into this router. There are two options where to send it to. And how can you attack this? So when the goal is to send it closer to the destination.
Can someone become a fake router?
That's difficult to become a fake router. But let's talk about it. Yes. So in a wired environment, not, because in a wired environment you would require that you have really these cables put out to other neighboring parties. But in the wireless environment, yes. So there has been also a very large community on ad hoc networks, wireless ad hoc networks, where basically the messages. So all these routers are mobile people with their smartphones or so walking around, and the idea is to hopefully have somebody in the range that you can send it to, so that they have somebody in their range to send it to, so that you can send your message from A to B. And in this case, some people can fake to be routers for domains that they don't manage. But in the wired world, maybe. So it's more difficult. But what they could do is, so let's say this network has some kind of IP address range, I don't know, 177 and then something. And it could also claim, it could falsely claim that it's also available for this IP address. And it announces it into the network that all packets for this IP address are also processed by this specific router and this specific network. So it can try to attract messages that are not intended for itself. So typically what we have in the networking environment here in this level is exactly that let's say if the nodes want to forward the messages as far as possible to the destination, if you take influence on what is the fastest path, then you might create paths that are not valid or that are longer, and this kind of attacks. Or as in this case, that you can try to take over traffic by your network that you are not responsible for. We will also look into these options. Okay. So yeah, what I wanted further to talk about is to see what kind of layers. So do you still remember the ISO-OSI layers or the layering of in the communication networks? Yeah, this most important thing about networking. So how the elements are set up. So first of all, in the physical layer, we have the bit transmission basically. So it's about one bit, how to transfer it over one network cable, this twisted pair cable, or one bit how to transfer it over the air, or how to transfer one bit over fiber optics cable. So that's basically the physical layer, how bit transmissions are realized over copper, over over air, and so on. Okay, so this is step number one, layer number one. Then we are looking at the one-hop connection. So let's say if we are able to encode one bit over the air, how do we organize the medium access, let's say, to the access point? So if there are so many smartphones now in the room and there's one smart access point somewhere, how do they organize that there's only one talking at one time? So if there are, in this case, I don't know, n participants, 30 participants, only one is allowed to send at a time. And because what we can do, we can already send zeros and ones. That's already good. Now we can coordinate who is able to access the network to the single base station. And the next point is, so this is one task, and the second task is data as a link layer. So basically to take these zeros and ones and to put it in some kind of format, a so-called frame, that is somehow interpretable, and both parties that send this frame, in this case it would be this way somehow, it's probably not the best example, but they make sure that all of the bits that have been sent are arriving correctly, and this one single hop has been done, it has succeeded. So there are no bit errors, the message has been delivered to the next hop, and it's really important that this one single hop works properly by using the ability to send bits. Okay, the next step is when we can send one hop, then we can send one hop here and one hop here and one hop here, and basically an end-to-end route for host-to-host communication is a set of consecutive one hops. As we knew from what we assume here, one hop is successful. So one hop, there are no bit errors, every one hop communication succeeds. If it did not succeed, then it's resent, but only on this one hop until both parties on one hop communicate that it has been received. So now we can have everywhere one hop communication, so we can address multi-hop. This is what's done here in the routing, in the network layer. Basically, we have got the task to address nodes in the network. So now this is A, this is B. Can be in different continents. The routing has to take place. So if we want to route from Bingen to Sydney, then the shortest paths to the destination must be known. And every individual router that gets the message in has to decide in which direction to send it. That's forwarding. Okay, this is the network layer. So now we come to the transport layer, and now the abstraction is A could send a message to B. But on B, there are various programs running. So here's a web server, there's an email server, there's a chat server, I don't know. And here there are also various applications running on A. There's a browser, there's an email client. So what do we have from what did the network layer provide to us? It provides us the end-to-end communication, so we can send a message from A to B, and we use it for in the transport layer in order to address applications on the hosts. So in this case, the browser sends a message not just to B, but to the web server of B. So the web server has its own address on the machine of B, and this is signaled by the port number. So if our browser wants to send a message, then to the web server at the port 80 on IP, node IP of B. And then finally, so that allows us to communicate between, let's say, the browser and the web server, and the application layer then allows us to define what these messages mean. So what should be the content of the messages. And then here's our Chrome browser and Apache. Okay, and why I have this slide also here in network security, because obviously all of these layers and every layer, the functionality of that specific layer can be attacked. You can have attacks on the bit transmission, you can have attacks on the media access and data protection. And before, let's talk about potential attacks. That's maybe not bad at this point here. Let's pick this up, because let's assume all of these tasks that we looked at, how have they been initially programmed? So the first time ARPANET around the 60s, this were basically several universities that were, of course, collaborating. Everybody was hopeful and optimistic and trying to build a network so it's like building a network at your home where you trust yourself and your other family members also that they don't run attacks. And basically it was first a small network of a few university colleagues, and then it grew to other universities, and then it grew further on. And basically at the beginning the focus was on providing functionality. You can connect, you can send messages, you can send emails, great. But then it was open to everybody, and everybody's not nice. So there are people that are not nice, and especially security was not planned in from the beginning. And now we have to think what could bad guys do with the network, especially in all of these different layers. And what can we do in order to comprehend this? And the problem is always, if there are n problems and ways to attack a network and to attack some kind of service in the network, the attacker only has to find one, and the defender has to n defenses. So the defender has to close all doors, and the attacker only has to find one open door. So it's really a more difficult task for the defender, obviously. Okay, and what can be protected? So one of the examples we already had, when it's about connecting to the access point that we don't know how to identify. So first of all, authentication. That means proving you are who you say you are. So if you connect to somebody, you want to know who is that. If you connect to a web server, let's say at Amazon, or let's say at your bank, and you type in your bank account credentials, and that basically verifies towards the bank who you are, you would also like to know, is that really my bank? Because otherwise you hand over your credentials to somebody who can use it to log into your bank, and that's probably something you do not want. So authentication is proving your identity. Confidentiality, that we also talked about when it's about the wireless communication, let's say, and every message you send out can also be received by everybody else in the environment. But confidentiality means that data can only be read or heard or understood by authorized subject. So the recipient, typically. Recipient, is it right? It is quite general, therefore it's written red, because of course if you store the data, that also still applies. So it doesn't make a difference whether the data is sent and currently on its way and in the network. So it can only be listened to authorized subject, or whether it is stored afterwards and it's only read by authorized subject. So only authorized subjects or individuals should have access to the data. But obviously we have the challenge that still you want to send it somewhere, so you need some mechanisms how to modify the data that the recipient can read it and others not. Yeah. So one question with regard, so here it's written guaranteed via encryption, symmetric or asymmetric. So because this will be some quite some question how far I should repeat this. So symmetric encryption, I think who of you are familiar with how symmetric encryption works? Okay, that's good. And asymmetric, I would assume the same people, asymmetric encryption, okay. Okay, because there are 3 building blocks for network security, basically. Yeah. 3 main building blocks. That's symmetric cryptography, asymmetric cryptography, and hashes. Yeah, basically hashes. So these 3 we need to then repeat. That would be essential. Okay. But first, picking up the third main goal, that's integrity. And that means that unauthorized changes to the data or the message is detected. And quite interestingly, so we just, I think 2 months ago, we wrote the lecture on IT security. And if I remember correctly, that was also one question: what is data integrity? And I think everybody except one or two had this answer wrong. Because most of the people say data integrity is that you cannot modify the data so that it's strictly enforced in this state. But it's not. So every data can be modified. Actually, everything is just bits and bytes on the hard disk. And modifying data is simple. The trick here is that unauthorized changes are detected. Yeah. Because if you send a message from A to B, this is the message and it's going to B. Everybody on the way could, so you have your text and somebody modifies it to, I don't know, TTT. So it replaces the X. Everybody can do it on the way. So it's no problem, it's just bits. But B should be able to detect that the modification has taken place. That can be done, this will also repeat, via digital signatures and detect tampering. So here the hashes will play a very important role, and what hashes are, hash functions, we'll talk about. And these are basically the CIA elements. So authentication is somehow the most important one, because it is the basis for confidentiality and integrity. So you need to know whom you are dealing with in order to decide whether this is an authorized subject to read or to write data. And there are also other elements such as access restrictions, more network related, but basically this is authentication related, or firewalls, which basically both elements talk about how to block participants from the network if they cannot authorize themselves, they cannot authenticate themselves correctly. So let me just, yeah. So maybe to go through yeah. I still want to talk a little bit more about these layers and what layers we have. So first of all, why do we have layers in networking? And later you will find that also the security solutions and the problem descriptions are according to these layers. So networking in general has some very kind of big challenges. So how to connect to the network, how to modulate bits, how to find the shortest path, how to make sure that messages are not that are resent if they are lost, and so on. So therefore, for easing to find solutions in this domain, there's this reference model, and hopefully all of you know this: the physical link, the physical layer, the link layer, the network layer, transport layer, application layer, and what they all kind of tasks they have. I would like to talk, starting from the bottom. We can emulate bits, so zeros and ones, nothing more, just individual bits. Then we use this to build some kind of frames out of them that have some specific structure, especially that allows us to have this reliable one-hop communication, so that really this kind of bits, as they have been sent, are really transferred at the other side of one-hop communication. And medium access is there also. Then the network finding the shortest route, the shortest ways. Transport layer protocols, that's basically where you allow processes to communicate. So on one machine, on one host, You have the web server, the email server, the DNS server, whatever, at the server side, let's say, and on the client side, we have a browser, we have DNS client, we have an email client, and now the processes on these machines can communicate. And the application layers, how the protocols itself look like, so what requests we might have in HTTP GET, and what the answer could look like, and so on. Yeah, I don't go too much into detail. I just yeah. So, okay, let's quickly go through it. So basically, the application message has its clear demand. Let's say this is a GET. It is according to HTTP 1.1. I think there's a slash, and then index.htm or so. So there's a message that is specified on application layer, and this is handed over to the transport layer with the request, please deliver it for my browser. Basically, it has an individual port number. I don't know. So it's this browser wants to communicate to this web server 80, and the information related to the transport layer is added into the header of the transport layer. Then what we also need is to address by IP addresses, and this is also added. This is then also added as a header, basically the addresses of the sender, of the recipient, also of the destination, and so on. And this is still host to host. So basically we want to enable end-to-end communication from the source. Where's the source? Let's see, here's the source, to the destination by using the link layer, which allows us to get one hop wide. So we also put the addressing information in the header, and then also for this one hop communication, if we had this multi-hop at the network layer side, for the one hop, there might be different other recipients in the sending range. So we also need some addressing here. We also need to make sure that the packets, the messages are arriving without errors, and because this is very important part, so that basically the one hop communication is working properly. And then at the physical layer, if it's really about bits and zeros and so on, we also have potential damages there, what can happen. It's like really putting the original message in a segment of TCP, let's say, to putting the segment in a datagram to be sent over IP and routing, and then at the last hop to take out the frame. That's the smallest, basically what contains it all, and delivering it to the destination. So basically you take the message, you put it, you add some header to it, then it becomes a segment. Then you put some header to it, then it becomes a datagram. At the one hop level, it becomes a frame. It's delivered to the next hop, and typically it's like this, that only the end devices, the transport and application layer are processed, and on the way it's either passing switches or routers. So on the one side, this is good because we can think of, okay, if the network influence only on these layers, what kind of harm can be made there? But also, of course, we have to think of the higher layer attack options. So basically, we have to think of all the layers that can have some impact on our communication. Yeah. Oh, it's very slow, yeah. Sorry. Okay, this is the. Okay, yeah. Okay, So what else do we need to know? Some words about addresses. Because as we have seen, we have addressing on various levels. So first of all, we have here, if our switch has different kind of potential other network, so what you can think of this router and the switch, if you think of an access point, then you have always in a one-hop communication range several potential next hop partners. So you have to on this link layer communicate to whom you want to talk. So you have your antenna. There's the node A, there's the node B, there's the node C, and your message addresses some kind of IP address. But this is you are currently at the layer where you want to just realize the one-hop communication. So you want to communicate to one specific of these recipients, but you need to be able to address it directly for this one-hop communication. And basically there you have to use the physical address, or it's actually not physical address, it's the medium access layer, medium access address, which looks like this pattern that is permanently assigned to not the these are too many, so not to the device, but to the network card or so. So that kind of device. Let's keep it this way. So if your machine has let's say 5 network cards, one Wi-Fi, one Ethernet, one USB-C or so, then every of these network cards has its individual physical address, this MAC address. And in case that somebody wants to send a message to it, if you have this connected, so this simple connection approach with just a simple cable, and the MAC addresses here is A and B, then you still have to use the addresses. And if you have this kind of wireless setup, then you have to announce this message that I'm sending is addressed, so the MAC address is that of A, and you have to give it so that all other participating and listening nodes can identify by receiving the first bits that they are not addressed, and then they switch off for a while until the message is sent and just A is listening and capturing it. That's that's the planned approach. So this is how typically, if all of them receive the same message, everybody checks, is the message addressed to me? If not, I go offline for the time of delivery. I can save some energy, and just node A receives the message. Then for the multi-hop communication, then we have also some IP addresses. So this is then basically how the source and the destination are in general addressed. So these are, for example, local addresses. These are all local IP addresses. I mean, they have this typical pattern, 8 bits, so from 0 to 255. Another number, another 8 bits. And so for IPv4 we have 32 bits. For IPv6 I think we have 128. And so there's much more information to carry. And basically this is the information. So these are local addresses. But if we would have some address, I don't know, 1, 3. Then this is in the internet the address that is globally routable. So basically any device in the internet can send a message to this one, and every router in the middle, so just jumping back, where do we have the routers? So these routers in the middle receive a message addressed for this, I don't know, this IP address. And it might be here, and it doesn't matter where the message comes in for this destination. it finds its shortest path to the destination. So IP addresses are quite important. And the port numbers, well, I've seen there quite less attacks on that. Basically, the idea is if you have A and B connected through the internet somehow, and the networking has been successfully, then you want to address, to give the option that the browser can communicate with the web server. It's basically representation of the ports, the task IDs, and so on. Okay. Let me just see. That's good. Okay, let's do these 2 slides. I just want to sketch out what kind of. So please have a look whether you are still familiar with these kind of protocols that are typically discussed in the networking lecture. We will also go through them a little bit, but these should be known. So the ARP protocol, DHCP, DNS, file, FTP, not maybe, HTTP, yes. This is so these protocols should be somehow familiar. This is that we will check. No. This we will look at. IMAP, this we will not look at. Telnet, this is a program that we will look at. And SCP, UDP. So these protocols should be roughly, with the check marks, should be known. And I'm aware that there are so many protocols, but at least those in the main domain should be known, and also in the application of some of them. Okay. So next time we will also go through a little bit more about security to have the same basics. Today I will work on the lab exercise to put it online. Please check it. If tomorrow it's still not accessible, you cannot download it, then please tell me. Again, have a look. Let me just show you where you should have a look. You should be able to register for one of these dates. And the lab material will be available here at least. So that should work. And then see you then on Thursday. Bye.